going to read this question and find what are we given in question number 2. So I'm going to make sure I review the basic things that we need, all the basic things that we need. Okay, so I'm pulling up a whiteboard, and as I read this question, I'll put the in this whiteboard. All right, question number 1. A university says that the mean number of classroom hours per week for full-time faculty is 11, which means it says 11 hours. The mean number of classroom hours per week, so that's weekly, for full-time faculty is 11 hours. So every week, the mean is 11 hours. So remember, it is mean. We're talking about mean. So we already know that this is a t-test. How do we know it's a t-test? Okay, let's keep reading. We'll find out why it is a t-test. But the mean number of hours a week is 11. Okay, so that's the mean we are contesting. All right. Okay, a random sample of the number of classroom hours for full-time faculty for 1 week is listed below. How do we know that it is a t-test? So we're going to leave, if we count all this, it means the number of faculty. So 1, 2, 3, 4, 5, 6, 7, 8. Therefore, sample size is only 8. Therefore, they are sampling only 8 faculty. 8 of them. Sample size is 8. And what is the alpha, level of significance? The alpha is 11. I mean, 1%. Is it 1% or 0.01? Let's check. Okay, the alpha is 0.01. Sorry, 0.01. Alpha is 0.01. 1%. And what else are we given? And then we're given raw data. That's it. In other words, because we're given raw data, we're also given sample standard deviation. So we don't even know the population standard deviation. In other words, sample size is less than 30, and we don't know the population standard deviation. So the first thing we want to do is put this data in our calculator. As soon as we put it in our calculator, we check for 2 things. We're going to check that the data is normally distributed. If it is not normally distributed, we cannot do inference. So I'm going to put the raw data in my calculator, and then I want to put this data in L1. So I'm going to clear enter. This kind of question will be in your test already. All right, I want to put the data, the number of hours taught by these 8 professors. I want to put it in L1. So 11.8, 8.6, 12.6, 7.6, 6.4, 10.4, 13.6, 9.1. So this means that one of these professors taught 11.8 hours a week. Another professor taught 8.6 hours a week. Another one taught 12.6 hours a week. Okay, so that's the number of hours they taught. And I want you to know that you can have fraction of hours. Somebody can teach a fraction number of hours. Some of them could be office hours. Some of them could be you did not finish a class on time. You were teaching and students had questions, or you had to finish some things that are important. Okay, so sample size is 8. My calculator is asking me for the 9th. Means that this data, I have enough of them. This is the right one. I have to also eyeball what I entered. There doesn't seem to be any mistake. So the first thing I want to do is to draw a modified box plot to check and see if this data is actually from a simple random sample. Can I do inference? One of the properties of t-distribution is that the sample you're doing inference with must be from a normal distribution. So second, so I'm going to, and I'm going to turn this on. I will, now I am selecting this number. The one I'm selecting, the chart I'm selecting is called a modified box plot. A modified box plot is used to select outliers. So it deselects outliers. What does it mean? It means that if I graph this sample raw data, if I graph this raw data and the modified box plot connects it, all of them, then there is no outstanding outlier. There is no outstanding outlier. So that is what I do whenever I'm given a raw data to do inference. Whenever I'm using a raw data to do inference, I must check the data to see that it does not have an outlier. So that's what I'm going to check now. So the data is in, I have selected modified box plot to check for outliers. Data is in L1. Frequency, I don't have frequency, so I'm going to put alpha 1 because I don't have frequency. It's a raw data, a simple random sample right there. So everything looks good. I can now say zoom 9. Before I say zoom 9, I'm going to check and see there's nothing, no function in Y1. Okay. So I am going to zoom 9 and see. Zoom 9. Well, this is the modified box plot. It's all connected. The modified box plot is all connected. Therefore, the data is not from, it's actually the data is from a normal distribution, no outliers. Another thing I can do is one variable start. Go back and do start, one variable start of data in L1. And then I'm going to calculate. So in this calculation, I see that the mean of this data is approximately 8.776. So the mean is 8.76, and the sample standard deviation is 3.71. So mean is 8.76, and the sample standard deviation is equal to, the sample standard deviation is this S of X, and that is 3.71. And that's all I need, 3.71. Okay. Okay, so the next thing I want to do, I can start the statistical test immediately. So I'm going to start. What are the steps? There are 5 steps. You can make them 6 if you want to. There are 5 steps in hypothesis testing. So I have done the preliminaries. The conditions are satisfied because the data is from a normal distribution. So I will state the claim. Step 1, state the claim. Stating the claim means writing the null and alternative hypothesis. Null, the mean is equal to given to me, the mean that is given to me is 11. So the mean is 11. The alternative hypothesis says that the mean is, why am I going to say that it's a two-tailed test? It's not equal to 11. Let's go back. Let's find out why it's a two-tailed test. They told me that the number of classrooms per week, full-time instructors is. So the keyword is. It means it could be greater or less. So the keyword is means if it is not 11, it could be greater than 11 or less than 11. So step 2 in hypothesis testing. So that's step 1. Step 2, identify alpha. And I'm already given alpha. Alpha is 0.01. This is a two-tail test. Therefore, I'll find alpha over 2. I'll divide alpha by 2. That tells me that I have a two-tail test. So 0.01 divided by 2 is 0.005. Step 3, calculate the critical value from alpha. So I'm going to do inverse t. Inverse t. Why inverse t? It's a t distribution. Inverse t, area to the left is 0.005. Sample size is 11. Actually, sample size, let's count. Sample size is 8, sorry. Sample size is 8, n is equal to 8. And degree of freedom is 7. Degree of freedom is sample size minus 1. So degree of freedom is 7. So I'm about to calculate the critical value right now. So calculate the critical value, get my calculator out, find the critical value. You have to be able to do a whole lot of them. You should be able to use the calculator. You should be able to the steps, apply them while using your calculator. Okay, so if you know how to use your calculator, but you don't know how to get the steps, it's a problem. So where do I see inverse t? So second distribution, number 4, area to the left in decimal is 0.005, 0.005, because it's two-tailed. Degree of freedom is 7 because sample size is 8. Degree of freedom is sample size minus 1. And then I'm going to paste. Okay, therefore, the critical value is negative 3.4. I can just say negative 3.5. Okay, so T alpha over 2, that's a critical value. T alpha over 2 is negative 3.5. Okay, approximately negative 3.5. That is the critical value. Okay, so the next one is we want to 4. Calculate the test statistic. Test stat. Step 4, test statistic. Test statistic. Test statistic. You must know the formula even though you're using your calculator. The test statistics for t is t is equal to point estimate minus mean. The mean we are contesting all over standard error of t. Standard error of t is sample standard deviation of square root of sample size. Okay, so this is the test statistic. All right, so now I'm going to calculate that, but actually my calculator will also give it to me. So I can wait on my calculator to give that to me. All right, I'm going to conclude that here. So I'll pull my calculator and finish up. But I have also done steps 1, 2, 3, 4. Step 1 is identify the claim, which means state the null and alternative hypothesis. Step 2, step 1, identify the claim, state the null and alternative hypothesis. Step 2, identify alpha. It might be given to you, or confidence interval will be given to you. If it is given to you, then you have to divide alpha by 2 because it's a two-tail test. Why is it a two-tailed test? Why is it? Why is it a two-tailed test? Because the keyword says is implies equal sign for the null hypothesis. And if it is equal sign for the null hypothesis, and the keyword is, then it's a two-tailed test. In other words, that's going to be a right and left rejection regions. Okay, and we also found and then step 3, calculate the critical value from your alpha, and we did we calculated that, and it is this. Then step 4, calculate the test statistic. It is point estimate minus mean of the population all over standard error. Standard error for T is S over square root of sample size. Okay, so now we know what we have done. Now step 5 is the conclusion. Step 5, do the test and conclude. I am going to do the test with calculator, but I want to make sure that I found the p-value from my calculator. What is the p-value? When I finish, I will calculate p-value, and I'll compare my p-value with alpha. If p-value is greater than alpha, I will accept the null. If p-value is less than alpha, I will reject the null. And by the way, alpha is 0.005. Okay, so that is so I'm going to do the test in my calculator. But whether you do the test in your calculator or not, you still have to know the steps. If you don't know the step, you cannot proceed, because you have to know what to tell your calculator. You have to know what to feed your calculator. It's not just about doing the test in your calculator. Okay, so go to Stat, arrow to Test. And what kind of test am I doing? I'm doing a t-test, two-tailed t-test. Okay, what am I given? I can actually say that I'm given data. So I'm given raw data. Okay, what is the mean of that raw data? The mean is 11. And what is what is the list? The list is L1. Is it a raw data? Yes, it's a raw data. We are doing the right tail test. The right tail test. Actually, we're doing a two-tail test. Sorry about that. This is a two-tail test. My bad. Okay, then I like to draw those. So let me draw. Drawing helps me see what is going on. So the shaded region is actually the sum of the probability of rejecting the null hypothesis. And so now I found out that the p-value is 13 point, the total p-value, left and right. The total p-value is 13.18, okay? And the calculated test statistics is negative 1.771. So T here is negative 1.71. Okay. The p-value given to me is 13 point what? Let me go back and see what 13 point. So the p-value is 13. All right. Just need to stop misbehaving. All right. So the total p-value is maybe 13.2%. All right. So 13.2% is greater than 1%. The p-value is greater than alpha. So p-value is greater than alpha. Let me draw I need to draw the normal curve so that we can just, all right, we found the critical value. The critical value we found was, let's go back and see the value of the critical value from inverse T. So that critical value is negative 3.5 5. But you know, normal curve is symmetrical. Normal curve is symmetrical. So negative 3.5 on the left, 3.5 on the right. Okay. Negative 3.5 on the right and the left, and 3.5 on the right, and which means that the p-value, I mean the t-value, actually the boundary line is negative 3.5 and positive 3.5. What do I mean by the boundary line, by the way? It's called boundary line because the rejection region starts from here. This is the value of z that starts the boundary line at the left. This is the right. Okay, but I calculated the test statistics and it fell into the acceptance region. The value of t is negative 1.7. Negative 1.7 is inside the acceptance region. That's negative 1.7 right here. Therefore, according to the test statistics, I will accept the null hypothesis. Also, according to p-value, I will also accept the null hypothesis, HO, accept HO. So both of them, both p-value and the test statistics, accept the null, which actually means that we do not have enough evidence to reject the null. We do not have enough evidence to reject what the school is saying. See what the school said. A university says that the mean number of classroom hours per week for full-time faculty is 11 hours. Okay, so we do not have enough evidence to reject the university's decision. Our study, our calculations agrees with the university's calculation, what they said. We don't have enough. Why are we saying this? Because according to our study, the p-value agrees is greater than alpha, so we accept the null. Also, the test statistic helps us to accept the null also. Okay, so because this is a two-tailed test, we can also add one more test, and that test is confidence interval. That one more test we have to add is confidence interval. Therefore, does the confidence interval contain the status quo 11 hours? So whenever you're doing a hypothesis testing, you must, if it's a two-tailed test, you can as well do the test with confidence interval. So if it is a two-tailed test, then you can test in 3 ways. You can use the p-value to test. If p-value is greater than alpha, you accept the null, and we just did. You can also use the test statistics to test. If t falls into the acceptance region, you accept the null. We did in this particular case. Now we are going to, the next thing we're going to use is hypothesis testing or confidence interval. We can use confidence interval to do hypothesis testing whenever it's a two-tailed test. So let's do that. Whenever it's a two-tailed test, we can use confidence interval to do hypothesis testing. So let's go. Let's do that. Okay, so I am going to clean some parts, this side, that way I can do confidence interval. I'm going to use confidence interval to approve or disprove the hypothesis. But guess what? If the p-value accepts the null and the test statistics accepts the null, there is no way that confidence interval can reject the null. They all have to agree to do one thing. Okay, so let's use confidence interval. All right, so I'm going to draw a number line where the point estimate, X bar, is the midpoint of that number line. And this is going to be the upper bound of my confidence interval. And this is going to be the lower bound of my confidence interval. We have already calculated the point estimate, but it doesn't really matter. We are going to use raw data again. Okay, so let's use raw data, and then let's do the calculation. So we're doing the calculation. What are we calculating? We are using confidence interval to do hypothesis testing because it's a two-tail test. The only reason why we're using confidence interval to do hypothesis testing is because it's a two-tail test. So I'm going to clear, and I'm going to go to start. I'm going to go to test. This time I'm doing confidence interval for T interval. So I'm going to go down. Y interval. It's still going to be T interval because sample size is less than 30 and population standard deviation is unknown. So number 8 is a T interval. And I'm given data, so I want to use the data, the raw data given to me. Where is the raw data? It's in L1. Frequency is 1. What is the confidence level? The confidence level is 99% because alpha is 1. The confidence level plus confidence interval is equal to 1. So area under the normal curve is alpha plus confidence interval. Okay, so we calculate. Okay, so now the question we want to answer is, does the interval contain 11? On the left-hand side, we see it is 4.2, lower bound is 4.2, upper bound is 13.4. Lower bound is 4.2, upper bound is 13.4. Upper bound is 13.4. Therefore, the interval actually contains 11. 11 is somewhere here. The interval contains 11. The 11 is somewhere there. Therefore, we can now say, according to the test, given alpha of 1%, or you can say at 99% confidence interval, I do not have enough evidence to reject the null hypothesis. That is your conclusion. You have to conclude to the level of significance given to you, or level of confidence given to you. Level of significance is 1%. Therefore, the confidence interval is 99%. Therefore, I do not have enough evidence to reject the null hypothesis. In other words, the university's claim is correct. The university's claim is quite correct. Okay, so we do not have enough evidence to reject the claim. So this question is loaded because you have used all the parts of hypothesis testing to answer the question. You use confidence interval, you use hypothesis testing to answer the same question. Okay. All right, so let me go and make sure that this is not too